Sound waves. Question 7 from the March 2015 control test set by the Free State Department of Education. Physical Sciences Grade 10. Question 7. Anything that generates a disturbance in the air creates a pulse that travels away from the place where it is created. If the pulse enters your ear, it may cause your eardrums to vibrate, which is how you hear. Consider the following 3 diagrams that illustrate different sound waves on an oscilloscope. So that is question 7. We have sound A, sound B, and sound C. If you've been following this lesson series on waves, sound, and light, you should know that the diagram of a transverse wave and a longitudinal wave look very different. You'll also notice that the diagram of sound A, B, and C look like a diagram of a transverse wave. But we learned in the previous few videos that sound is a longitudinal wave. Why then are the diagrams showing a sound wave drawn like a transverse wave? When you connect a microphone to an oscilloscope, the microphone picks up the sound, and that sound is converted into an electrical signal, which can then be displayed on an oscilloscope. This is what a typical oscilloscope looks like. It is a device that allows us to capture the shape of a sound wave coming from the microphone. The microphone turns the sound waves into an electric current, which varies in voltage the same way the sound wave varies in pressure. Remember, sound waves are pressure waves. They have regions where the particles are closer together, which we call high pressure regions, and these regions are typically referred to as compressions. And they also have regions where the particles are a bit far apart, low pressure regions, and we call those rarefactions. Sound waves are made of alternating regions of high pressure and low pressure. This means that there's always an increase, decrease pattern with respect to pressure as we move from regions of high pressure to low pressure. Like I said, there's always that increase, decrease pattern as we move from compression to rarefaction to compression to rarefaction to compression to rarefaction. And this change in pressure looks like a sound wave. Increase, decrease, increase, decrease. So the oscilloscope does not draw the actual shape of the sound wave, rather the change in pressure of the sound wave. And that change in pressure is sinusoidal. This is why it looks like a transverse wave. If you did not follow my explanation, it is okay. The important thing is to know that sound is a longitudinal wave still, and that the oscilloscope just shows the change in pressure of a sound wave, not the actual shape of the sound wave. Question 7.1. Which one, A, B, or C, has the highest volume? Explain your answer. Volume is directly proportional to an amplitude. This means that the higher the volume, the larger the amplitude. So to answer this question, we must identify the sound with the largest amplitude. The amplitude is the distance from equilibrium to the crest of a wave, or the distance from equilibrium to the trough of a wave. The crest is the highest point on a wave. So if this is the equilibrium, the highest point on A is here. The highest point on B is here. And the highest point on C is here. This means that This means that the amplitude of sound A is from equilibrium to its highest point, and the amplitude of sound B is from equilibrium to its highest point, and the amplitude of sound C is from equilibrium to its highest point. If you look carefully, sound C has the highest amplitude. This means that sound C also has the highest volume. The amplitude of a sound wave is directly proportional to the volume. The larger the amplitude, the higher the volume. This is a 2-mark question. You will receive a mark for writing sound C and providing a relevant explanation for your choice. So we will say sound C has the highest volume because it has the largest amplitude. Question 7.2. The highest frequency that the human ear can detect is about 20 kilohertz. Humans do not hear all sound. We can only hear up to a certain frequency of sound. For example, we cannot hear ultrasound. I will explain more about ultrasound in the next video, so be sure to watch it when it comes out. Sound with frequencies above 20 kilohertz are called ultrasound. Question 7.2.1. Sound waves are longitudinal waves. Define a longitudinal wave. This is a recall question. You just need to have memorized the definition of a longitudinal wave. A longitudinal wave is a wave in which the movement of the particle of the medium is parallel to the direction of propagation of the wave. This is also a 2-mark question, and it is always important to mention the keywords. You should mention that it is parallel and that the two directions that we are concerned with, the direction in which the particle moves or is displaced and the direction in which the whole wave moves, are parallel, right? So it's always important to know which are the keywords in the questions, because those keywords are the ones that will get you the marks. Question 7.2.2. A certain instrument produces sound waves with a wavelength of 19 millimeters. If the speed of sound is 342 meters per second, determine if the human ear will hear this sound. In 7.2, it was mentioned that humans can only hear up to a frequency of 20 kilohertz. Anything above this value we cannot hear. In this question, we need to calculate or to determine the frequency that this instrument has. If the frequency of this instrument is below 20 kilohertz, then it means we will be able to hear the sound. However, if the frequency of this instrument is above 20 kilohertz, it means we will not be able to hear the sound. How do we calculate the frequency? Which expression or formula do you think we are going to use? You guessed it. We are going to use the expression for the wave equation, which is equals to the speed v equals to the frequency times the wavelength lambda. So in this instance, we are given that the speed is 342 meters per second. We are also given that the wavelength lambda is equals to 19 millimeters, and we need to determine the frequency, which we can essentially at the end convert to kilohertz so that we can compare. So as I've mentioned, that which expression are we going to use? We are going to use this expression over here. which says that the speed of a wave equals to the frequency f of that wave, as well as multiplied by the wavelength of that wave, lambda. And this is where your first mark comes from. So it's a 4-mark question. Your first mark will come from you providing the right equation or the right expression to solve the problem. But we are aware that we would like to solve for the frequency, not the speed. So it means we need to make the frequency the subject of the formula. How do we do that? We do that by dividing both the left-hand side and the right-hand side of the equation with lambda. So on the left-hand side of the equation, we have that the speed v equals is divided by the wavelength lambda. And on the right-hand side of the equation, we have that the frequency f multiplied by lambda is divided by lambda. Lambda divided by lambda is just 1. This means on the right-hand side, we will only be left with the frequency f. This is the same as just the lambda in the denominator cancelling the lambda in the numerator, so that you are only left with f. On the left-hand side of the equation, we still are left with the speed of the wave v divided by the wavelength of the wave lambda. So before we can determine the frequency, there's an additional step that we need to do. We need to convert that frequency or that wavelength that were given to us to the correct SI unit, which is in meters. So we want to convert from millimeter to a meter. And if we want to do that, it means that we need to divide by 1,000, since that 1 meter equals to 1,000 millimeter. So we were given that the wavelength of this wave equals to 19 millimeters. We need to convert that to a meter. Like I said, it means we divide the 19 by 1,000, and we will get a value of 0.019 meters. Now we can solve using the expression that we derived from the wave equation. So f equals to the speed v divided by the wavelength lambda. Now it is just a matter of substituting the correct value for the speed as well as the correct value for the wavelength, so that we have f equals to 342 divided by 0.019. And the answer that we get is that the frequency f equals to 18,000 hertz. So we have determined the frequency. Before we finish this question, let me demonstrate the mark allocation. This is a 4-mark question, and you already saw where the first mark is from. The second mark will come from the correct substitution, and the third mark will come from the correct frequency value, which is 18,000 hertz. So we know that we can write 18,000 hertz as 18 kilohertz. So we just divide 18,000 hertz by 1,000 to get 18 kilohertz. And when we've now converted our frequency to kilohertz, we are aware that 18 kilohertz is actually lesser than 20 kilohertz. Remember, the 20 kilohertz is the frequency limit, is the limit up to which we can hear. We cannot hear anything above 20 kilohertz. And therefore, this tells us that the human ear will actually hear the sound that the instrument makes. The important thing to mention there will just be that the human ear can hear the sound, can hear it, and then you get your last and final mark. Before we finish, please watch the next video to learn more about sounds that we cannot hear. Those are ultrasound, as well as the application where this unheard sound is used. Thank you very much.